Alright everyone, it's Mr. Reedy back with yet another video. Today we're going to talk about our final topic of Unit 5, which is on catalysts. And guys, a catalyst, or an enzyme in a biological system, is simply a substance that increases the rate of a chemical reaction, but is not consumed by the reaction. So it ultimately works by providing an alternative pathway for the reaction mechanism, and it lowers the energy of activation of the rate determining step. And as we saw in the previous video, right guys, it's that the higher the energy of activation for our rate determining step ultimately determines the rate of that chemical reaction. So if I provide a catalyst and it lowers that by providing an alternative pathway, obviously the rate of the chemical reaction is going to increase, right? So we can look at the effects of a catalyst through two lenses. We can use a Maxwell-Boltzmann distribution, which would be right here. And as you guys can see, normally our energy of activation is this red line right here. Okay, that's the minimum amount of energy needed for this chemical reaction to occur. Now, with the catalyst, all I did was lower this energy of activation. So I lowered it to about here. And since I've lowered it, that means there are more molecules that have the sufficient energy, and then therefore the chemical reaction will occur at a faster rate. We can also look at this in terms of our energy diagram. So if you guys take a look at our energy diagram here, we have two pathways here. We have the red pathway, which is the mechanism when it's not catalyzed, and then we have the one in blue, which is the catalyzed pathway, right? So as you guys can see, the energy of activation's been lowered, but just in case we need to spell it out, this would be the energy of activation for the uncatalyzed pathway. As you can see, it's pretty high, so that is a very slow rate determining step, right? Now, with that catalyst pathway, if you guys take a look how much less energy is needed to surmount that reaction barrier. Well, since there's less energy needed, this chemical reaction is ultimately going to occur at a faster rate. So if we were thinking back to collision theory, right? Collision theory had, if we increase the temperature, a chemical reaction could happen at a faster rate. If we increase the concentration of the reactants, the chemical reaction can occur at a faster rate. If we increase the gas pressure for gaseous reactants, the chemical reaction would occur at a faster rate. If we increased the surface area of a reactant that is a solid, the reaction occurs at a faster rate. And then now, if we provide a catalyst, catalyst will provide an alternative pathway for that mechanism, thus increasing the rate of the chemical reaction. So all of those things can increase the rate. This video, though, is focusing specifically on the effect of a catalyst. Okay, so we're going to talk about chlorofluorocarbons and ozone again. And ozone has a slow rate of decomposition to form oxygen, as seen in this overall chemical reaction. So we have O3 reacting with some oxygen to form two molecules of O2. Now, guys, we want that, okay? We want ozone to have a slow decomposition because that's what's protecting our atmosphere. However, chlorofluorocarbons, which again is a greenhouse gas that you would see in air conditioners and refrigerators, actually provides a catalyst for this chemical equation. Okay, so this occurs because chlorine in the CFCs acts as a catalyst and provides an alternative mechanism. So here's what happens when this reaction is catalyzed. So this chlorine here is coming from our chlorofluorocarbon. It's going to react to form ozone, and then it will form chlorine monoxide plus oxygen gas. That's the slow step. And then ClO reacts with oxide to form Cl and O2. Now, we need to add the two chemical reactions here to produce the overall reaction. And then we're going to determine the rate law for the catalyzed reaction. Okay, so first thing I want to do, though, is I want to go through and I want to identify the reaction intermediate. So our reaction intermediate is ClO. And the reason why we know it's ClO, folks, is because ClO is first produced and then it is consumed. Okay? So our reaction intermediate for this chemical equation is ClO. Now we need to find our catalyst. And the catalyst, guys, is the exact opposite. So a catalyst is going to be first consumed, then produced. So if we take a look here, our catalyst is going to be chlorine. Look at chlorine is first consumed, and then it is reproduced in step 2. So the catalyst for this chemical reaction is in fact the chlorine. Okay, again, consumed, then produced, that's a catalyst. Where an intermediate is first produced, then consumed. Okay, so just keep that in mind as we go through this. Now it wants us to add the elementary steps for this chemical reaction. Well, our elementary steps, we're going to, of course, when we add these two up, what we end up happening here is the chlorines end up canceling out. And our intermediates end up canceling out, and we're left with O3 plus O yields 2O2. Okay, perfect. So we got the overall chemical reaction as seen. Now, guys, you will also see catalysts put over the reaction arrow. So if you see this, that is also a correct way to do that. Again, sometimes you'll see a chemical reaction with something written on top of the arrow. We've actually seen a couple of problems that have had that. That's just the catalyst. So we could put chlorine as the catalyst on top of the reaction arrow to signal this. Now, because a catalyst, I'm jumping ahead here. So we know we have to write the rate law with respect to the slow step. So I'm going to say the rate is equal to the reaction constant K. Times the concentration of O3, because O3 is obviously our reactant. Now, because a catalyst ultimately affects the rate of a chemical reaction, guys, we have to include it in the rate law. Okay, because if I increase the concentration of my catalyst here, right, if I were to increase it, the rate obviously is going to increase. So catalysts are represented in a rate law. Super important here. So a catalyst can be represented in a rate law. Okay, super important there, guys, to consider. Okay, let's continue on now. So here is actually what's happening with the CFCs in the ozone. As you guys can see, our chlorofluorocarbon is going to break down from UV light from the sun. That free chlorine atom is going to hit the ozone molecule, and it causes the chemical reaction. Now, as you guys can see, ultimately what's happening throughout this mechanism is that chlorine is being first consumed in the first step, but by the end of the mechanism, another chlorine atom has reformed, and it can then do the same thing to another ozone molecule. Now, guys, this is not, in all case and purposes, not a good thing for environmental chemistry. CFCs, because of this, it's the chlorine itself, again, is going after our ozone. As you guys can see, every time chlorine is used up, it produces another chlorine at the end, because catalysts are again consumed, then produced by the end of that mechanism. So this chlorine can go find another ozone molecule and repeat the process over and over again. So in some cases, a catalyst is not beneficial for a chemical equation. Okay, and as you guys can see here, I have the transition state of the normal chemical reaction is much slower than the catalyzed pathway. And you'll see that the catalyzed pathway, of course, has two transition states because the intermediate, right, this hump here is the signal of where the intermediate would be undergoing a chemical equation, okay? Again, they ultimately produce the same products. However, a catalyst will be consumed than produced, okay? Now, there are two different types of catalysts, guys. We have homogeneous catalysts, which is a catalyst that is in the same phase as the reactants. So from our previous example, that would be chlorine and ozone. They're both gases. A heterogeneous catalyst is a catalyst that is in a different phase from the reactant. So catalytic converters, which is in your exhaust system of your cars, consist platinum, rhodium, or palladium on high surfaces with ceramic to convert the exhaust from the pollutants. So if you guys take a look here, we have carbon monoxide, nitrogen monoxide, NO2, and very large hydrocarbons being produced from your engine. Now they go through your exhaust system, and in here you have your catalytic converter, which, as I said, has platinum, rhodium, or palladium. And what that does is it provides an alternative pathway to produce less harmful greenhouse gases. So as you guys can see, it's producing water, nitrogen gas, which relatively speaking, these two gases are relatively harmless in terms of our atmosphere. And then, of course, carbon dioxide, which is much less dangerous than the gases that it started with. And again, so in this case, we're seeing a catalyst that is very beneficial. We need the catalyst in our exhaust systems to break down these more dangerous gases from the engine, being produced from the combustion reaction in the engine, okay? So again, catalysts, they could be beneficial, they could be negative, right? But ultimately, they achieve the same thing. They are speeding up the rate of a chemical reaction, okay? In biological systems, catalysts are called enzymes, okay? And they're usually very large, three-dimensional proteins. And in a catalyst, we have two different things. We have the active site, which is the area on an enzyme in which the catalyst occurs. And then, of course, we have a substrate, which is the reactant molecule of a biological chemical reaction that binds to the active site of an enzyme. So here's our substrate. Let's say it's, this would be sucrose, let's say. So this is sucrose here. It goes on to its enzyme sucralase, which is the active site. So then once they fit in here, the enzyme is able to put strain on the bonds, and it produces fructose in one side and glucose in another. Okay, so again, substrate is the actual reactant, right? That is going to be catalyzed from the enzyme. Okay. Now, when the enzyme and the catalyst are together, we call that a complex. And as I said, after the catalysis occurred, we have formed smaller molecules. Back to what I said in the previous video, guys, this is how these very complex biological mechanisms, so in glycolysis as an example, glycolysis has 8 steps to turn glucose, C6H12O6, into pyruvate, okay, which is a much smaller molecule, which allows for obviously a more complex reaction to occur. So there's a series of 8 steps, and each of them needs about an enzyme to do it, guys. Now, enzymes go through something called the lock and key model, which is a substrate binds to a very specific active site, and then they can undergo a chemical reaction. So guys, to put it nicely, the lock and key model basically has every enzyme has a specific shape, okay, that is the correct shape needed for the big sugar molecule, the big, the big fat molecule, the big protein, whatever it is, protein, lipid, or sugar, okay? The active site will actually look like the shape of that molecule. So then that molecule can go in. So again, let's just assume we're talking about sucrose breaking down into glucose and fructose. The active site here of sucralase matches the shape of the sucrose molecule. So the sucrose molecule comes into the active site. As it binds, it forms the enzyme substrate complex. Right here, a strain is placed on the bond, keeping glucose and fructose together. The enzyme substrate complex, sucralase, will break that, and then we're able to form glucose and fructose, respectively. And with that being said, guys, that is the end of today's video, as well as our end for our kinetics chapter. If you have any questions, please shoot me an email.